We had a request for Fall 19 Test 1 Part 4 mechanisms. Question 3. And on this page, when I get over here, we're going to go red first, blue second, whatever else third. But over here, we can't do that. You do need to cross off your spectator. With a Grignard, it's both the BR and the MG. Here it is. You want to see it? One of magnesium's cations is canceled by the BR, and the other is still a cation. There you go. There's your spectator. I crossed it off. Don't forget, the thing attached has lone pair and minus. Don't throw away a half point by forgetting the minus. You're going to attack the carbonyl, make pi, sorry, you make pi into lone pair. And we already have a short form for that. And you're almost done. Very simple mechanism, the Grignard addition to aldehydes, ketones, or even epoxides. They have the same level of difficulty, all three. Same number of arrows, same steps. Now we're doing oxidation of a secondary alcohol. First step is to activate the chromium by protonating. Second step is to attack it with the poor nucleophile. Different color. Can't do it before you do the protonation. Attack the chromium. Oxonium gets neutralized. Third step. Oh my goodness. I'm putting the H on here. When you do this step, you generate sulfate ion. OSO3H negative. That's after step 1. Some third color. And right now, you're going straight to CO isopropyl chromium with a double bond on top, OH to the right, O with a new H to the bottom, and an OH to the left. We have a new bond to O as well. This thing needs to become a chromate ester, which we will do right now. Remember, sometimes if you're stuck, knowing what you need to go to is just as good for clues. You need to go to this, where chromic acid looks like chromic acid again, except you've lost water, haven't you? So how do you get there? You got to make an O leave. It's elimination. But you have to make one of the OHs leave first, and it's not ready to leave until it's protonated. So step 1, protonate one of the O's. In doing so, you will generate OSO3H negative. So you pick one of the O's to go. As I drew it, it looks like this O corresponds to the one that got lost. Protonate it first or else it won't leave. Step 2. Yeah, make it leave. Baby blue. Baby blue, making it leave. Well, you got to pick up a proton from here, make a pi here, leaving group leaves. There you go. You got water. You want to see it? Water. Lone pair. Now, how do you get from there to there? They look almost the same, don't they? And I have my clue as promised here in this one. I'll try to remember to put that clue on there. Water needs to become hydronium. Grab an H. This needs to lose one of its O's. Keep this H. Looks like this bond's got to go. So what H am I grabbing with water to make it into hydronium? Well, there's no H drawn on the page yet, so you got to draw it for me first. Where is the H that needs to go away? Which carbon has an H that needs to go away? Describe this molecule and tell me which carbon on this molecule has an H that needs to go away. The one with the O is all I needed to hear. Thank you. There is no H on the carbon here, which is the same as the carbon here. It has to go. You don't need two colors for this one. Grab H. Sigma becomes a pi. This leaving group leaves in a reduced form. And there you go. That took half the writing as if I didn't use shortcuts. So Monday's lecture, we had one without shortcuts. Or maybe it was the Sunday special lecture. One of those two. And it's in the lecture notes. And here is with the shortcuts. Now maybe now we can start using shortcuts more. Hey, guys, if you're not ready for shortcuts, you don't have to pretend to be ready for shortcuts. It's okay. You can get full credit without ever using a shortcut. All right. Bye-bye.